All right, everyone. So my name is Sean Devine, and I'm a technical sales specialist for Global Test Supply. Thank you very much for joining us today for this webinar via our Global Test Supply University. Today's topic is going to be on UPS and battery maintenance in partnership with Fluke. We kindly ask that you're going to mute your microphone during the presentation. The presentation will last about 45 to 50 minutes, and then we'll have time at the end for a Q&A. We encourage you to ask your questions at any time. Simply use the chat feature, and we'll get to your questions at the end of the presentation. Global Test Supply has been working closely with Fluke for many years. We pride ourselves on being a leading distributor of Fluke. This is a result of our dedication to offering you our product expertise, service, and competitive pricing. Let's get started. Today's webinar is going to be presented by Dave Robley from Fluke. Dave has been working with Fluke since 1984, recommending test equipment solutions for customer applications relating to thermal imaging, vibration testing, power quality, electrical measurement safety, and motor drive troubleshooting. Dave has a level 1 certification in both infrared thermography and vibration analysis. And Dave holds a BSc from Marquette University and currently works as a sales applications manager based in the Chicago area. Dave, thank you so much for joining us today. Please take it away.
Thanks, Sean. Appreciate that. And on behalf of Global Test Supply and Fluke, we appreciate you inviting us in today virtually. So let's take a quick look at our agenda. We're really going to be splitting this up into two main portions. One where we're going to be focusing overall on the UPS, and we'll be discussing really all aspects around that, from first-time commissioning to ongoing maintenance to troubleshooting and investigating different types of tools, instruments that are useful to be able to, in each of those three phases, to be able to determine the health and functionality of your UPS system. Of course, a critical component of any emergency power system is batteries, backup batteries. So we'll use the other half of our time to really talk a little bit more about batteries in particular, battery technologies, and if we were to assess the health of our batteries, what are some of the standards and test guidelines, and what measurements are best to make to determine health, and what tools are in the best position to make those health measurements. Let's start with our UPS system as a whole. Obviously, those types of systems are everywhere: data centers, hospitals, airports, utilities, oil and gas, railways, anywhere where you absolutely need 100% backup power reliability. Even standard commercial and manufacturing facilities, they have backups power systems for their distributed control systems, alarms, emergency lighting, steam systems, wide variety. So as such, they're absolutely mission critical, and it's in everybody's best interest to make sure that they're installed properly, maintained properly, and then if there is an issue, to be able to troubleshoot it reliably. So UPS system, just kind of a brief block diagram there. Really, it consists of your normal AC power source feeding into a charger, providing a DC voltage and charge current to batteries, which we'll be covering really in the second half of this, and then going off to an inverter to convert from the DC of the battery back to AC to reliably power our loads. And these go through things called the static switch, and as well as a manual bypass switch that would engage maybe bypass power source such as a standby generator, all to keep those critical loads up and running. So we'll take a look now at what are some of the tools and techniques for, again, that commissioning, maintenance, as well as troubleshooting aspect. I think the first thing, and it makes sense to look at this first, is really looking at thermal imagers or infrared cameras. I'll use those terms interchangeably. I think many, if not all of you, are somewhat familiar with thermal imagers, but essentially what they do is they sense or can measure infrared energy that is literally emitted by everything on the planet. And they can take that infrared energy, convert that to a temperature. So these are measurement devices. And then from a series of temperatures across the field of view, they construct or build an image of what you're looking at in terms of heat. So oftentimes heat can tell you a lot about the health or unhealth of something. So when we think about our UPS systems and you think about all the electrical components that are involved, batteries that are involved, there's a list there. Circuit boards, transformers, components, fans even, cooling fans. So there's a lot that that can go wrong. So I think a thermal imager, infrared camera makes a great screening tool to make sure that everything looks good when you've commissioned, just on a maintenance basis. It's a fast, non-invasive, quick screening tool to be able to, if not tell you exactly what the problem is, point out something that doesn't look right, that requires further investigation. And we've got some sample images here. And so you can see these pictures in terms of heat. And when it comes to a screening approach with infrared cameras, really you're looking for something that doesn't look right. So it's really a lot about what is the image actually telling me. So if we look at a few of these a little bit closer, and these are examples that were from the list before. Something as is evidenced here would be what looks like a hotspot here at a termination or a connection. And it looks like as you move up the conductor or the wire away from this, temperature gets cooler. That's a classic visual or a symptom of a loose connection or perhaps a corroded connection. So these are the types of things that you want to see. Perhaps overheated components on circuit boards. If this is a three-phase feed, you know that from three-phase experience, the load should be pretty similar on all three phases. This doesn't look right. Do we know what the problem is? Not yet, but the camera quickly was able to screen and tell us this bears further investigation. So again, use thermal imaging during the commissioning process, and then also in that that ongoing maintenance as a screening tool to rule out or rule in any issues that could affect reliable operation. What we have here is a kind of a diagram really of a typical contingency supply system for mission critical installations. So to help keep this system functioning as designed, there are certain tests that should be performed upon installation and then in a maintenance mode periodically, maybe monthly or quarterly after commissioning is performed. For both the ongoing as well as the commissioning, we're going to be really looking at two different stages. The first stage is called a pre-installation. So when you meaning before you hook up your critical loads down here, what you would perform or what you would use would be something called load banks. They can be resistive load banks, or it can be a combination of resistive and inductive to account for maybe power factor of your loads, your critical loads on site, or they could be capacitive. So, but essentially in the pre-installation phase, you're using load banks and not your critical loads. And then after, now this is all still part of commissioning. The second part of the commissioning stage would be where after your pre-installation testing, you would perform the same tests in what's called a combined test Combined meaning you're going to be actually, rather than load banks, you're going to be using and connecting your critical loads and testing while cutting the standby generator in and out. So as we look at these next tests, and there's 9 different tests we'll kind of briefly run through, keep that in mind that these tests will be used for both pre-installation as well as combined testing in that commissioning phase. So what tool is the best tool, or what kind of visibility do we need during these tests? So I'll be making reference to something called a power analyzer. What we have pictured here, our newest product is the Fluke 1777 power analyzer. It is a full 3-phase tool for voltage, current, and can make all the appropriate voltage, current, power measurements, power factor measurements that are required for the following tests. Plus, it has enough performance to be able to not just make measurements, but actually be able to catch transients as loads are switched, both load bank simulated loads as well as critical loads. So we'll examine that a little bit more, but this is an example of a full-featured tool that will cover all the bases for the required tests. The first test there is not actually a test you need to perform with a power analyzer. It's basically just a functional alarms test of the UPS itself. Just make sure things display. Does it go through a self-test properly? That sort of thing. So we'll really be more focusing on starting at step 2. So for the UPS specification test, really the purpose here is really to be measuring both on the input and the output side. So for this test upon commissioning, you would actually need 2 separate power analyzers, both which would be able to record the data for comparison and analysis then after the fact. So the process that you would go through would be really to record those following measurements that are listed there, everything about voltage, current, real power, apparent power, kW, kVA, power factor, but also look at both voltage and current distortion on the input and output to make sure it's within the UPS specs. And the process you would go through is vary loads, again, using the load bank in 25% increments. This would be first you'd run this test having balanced loads across all 3 phases. So go from 0 to 100% steps and then record the values. And then also you would repeat the test by using unbalanced loads. There's a process for doing that. It's actually 4 different combinations of load percentages on different phases. So for example, the first test would be on unbalanced. You'd have 100% load on A phase and B phase, 0% on C. Second, you would then put 0% on A and B, but 100% on C. And then for the third and fourth steps, you would put 100% on A and C, 50% on B, and then last step, 50% on A and C, excuse me, and 100% on B. So, and then again, recording all these, and the power analyzer does have memory. Also, you have capability of generating hard copy reports, especially from a commissioning standpoint. So next step then would be a burn-in test over time. And usually you would run the UPS at rated load with the load banks anywhere from 8 to 24 hours. And we show an example of that here. This looks like a trend over time of your voltages and currents over time. The next test is called a step load and bypass test. So what you're looking at is how does the UPS handle it when you you throw incremental loads at it. For example, going from 0 to 100%, and essentially what you want to observe is that UPS transient or short-term response to that. Does my voltage vary, when I hit it with 100% load? So these are the steps that you would take, and in each case, really what you're looking for there is, as say for example, 100% load current is thrown at the UPS. Do I have any voltage variations? And in these images here for the 3 phases, it shows that we do not. So this would be an example of a pass or success. Our next step, called start-stop test. So it's really more to show correct operation, when the UPS is switched on and off with full load in place from our load bank. So what you would do is switch the inverter on and off, and then make the same measurements as in the previous step with the power analyzer, record the transients, load voltage, load current, and then your incoming and outgoing mains current. The next test would be a loss and return of mains. So in this case, what you want to do is exercise the UPS, strictly run off a UPS for 15 minutes at full load, simulating a 15-minute power failure. And with a different type of tools, or maybe as part of your overall system, there may be a battery capacity monitoring there before and after the discharge. So that's really what you're looking at in that test. Next, it's called a loss and return of battery test. So what we're going to be doing is running the UPS module at normal rated load from the load bank, and then switch the UPS main output on and off. And here what we're doing is looking at our load voltage, looking for changes, recording transients, and we of course want to see our load current and mains current. And again, all these are, we're discussing them now in the pre-installation, which would be using load banks and for commissioning purposes. Our last 2 measurements that we make are really around load transfer. So what we would be doing is showing correct operation during a loss and during a return of the UPS batteries. So, or during the loss and return of UPS batteries. So you would turn switch the main battery breaker on and off, recording all the same types of measurements as we have in the previous few: transients, load voltage, load current, and then mains 1 current. And then lastly, what we would do is going to bypass and then back test, recording the same thing. So it's simulating that loss and return of UPS batteries. So it's run once with switching the UPS off and on until a static bypass, until the load is on static bypass. And then you would reverse the procedure, switch off and on to go to the UPS and record the voltages, load current, and bypass currents involved. As we mentioned, it's really 2 phases here for commissioning. One is pre-installation using load banks. If everything looks good after running your tests, then it's time to engage your critical loads with the combined test, and then also bring the standby generator into play. And this time you would repeat the same tests, but at 0 load and at 100% load conditions. So what we'd be looking at would be really the transfer between the mains supply, UPS, and standby generator to make sure that transients and waveform deviations are all within acceptable limits per the performance specs of the UPS. We looked at power analyzers as being that tool that provides great three-phase visibility to trending, all the right measurements, all the right power measurements, and then also for transient capture. We also do make portable troubleshooting tools. We call them scope meters, combination scope, which is short for oscilloscope, which will show signals or waveforms, and also meter in that it can provide automatic measurements. The scope meter is something that it doesn't have as wide a visibility. You have either 2 or 4 inputs, as is shown in the top graphic of our scope meter, one of our scope meters. However, they provide you to get the ability to get a little bit deeper visibility into some of the other circuitry, maybe away from the AC side. The power analyzers, they're primarily anything and everything related to AC. Scope meters can do AC, provide that visibility, but also look at other signals. So let's take a quick look at those. The first bullet, you can actually look at control inputs and outputs in the charger, on the inverter side, static switch. So you can troubleshoot more system components that are involved, that are a portion of the overall UPS system. And then if you do have some issues relating to or symptoms from a troubleshooting standpoint on your static transfer from the normal inverter power over to bypass power, you can use the scope meter as a waveform capture tool, visual tool, to be able to actually see that. And in this case, we have a 4-channel scope called our 190-504, 500 megahertz, so you can see very, very short rise time signals, great visibility in just about anything that you might see in a facility. And as we see here, the SCRs need to transfer from normal to bypass in less than 4 milliseconds. Otherwise, you could have power interruption to critical loads. So we actually have a graphic of that here showing both a successful crossover, as we can see if we're looking at voltage here. We can see that right around in here, we see a little bit, kind of a half cycle, little blip or a change, but essentially continuous power being provided to the loads. This would be an example of a failure. So this can be a great troubleshooting tool to, again, capture. You can set them up to trigger, capture these types of events, display to greatly speed up the troubleshooting. There's another method. You could also capture longer record length signals via scope record mode, record the entire event, then go back and analyze in detail. You can zoom in to actually view that switching time to make sure it's less than the 4 milliseconds. Lastly, these scopes have the ability, if you know or measure something, what does good look like, for example, on a good transfer, as is evidenced here, you can actually capture a known good event and then build an envelope, kind of that gray, defining above and below the amplitude, inside, outside that time window. We can actually do subsequent captures inside of a pass-fail envelope, and it can actually save any type of failure event or any type of pass event. So this is something that you can automate that testing, maybe even during the commissioning process, capturing the known good information. So in summary, our 3 areas, commissioning, maintenance, troubleshooting, and in each, there are different tools, technologies that would apply. Thermal inspections really can apply to all 3 because it's a great screening tool. You can rule out issues that might be causing some of the symptoms just by making sure that everything looks good from a thermal standpoint. Power analyzers really in all 3 phases can be used in Note that in the commissioning phase, pre-installation, essentially load bank testing of the UPS prior to connecting the critical loads, as well as the standby generator, and then the combined test. And Scope Meter makes a great troubleshooting tool. Quickly go out and do testing to get full visibility of all the signals that are in play. Now we're going to move to the battery portion of the batteries are at the heart, really, of all backup power systems. So wide variety of industries that we set up front, mission critical industries, from a human life standpoint in healthcare, from a data standpoint in finance, but human life, airport, wide variety, but it's also in use for battery backup and switchgear in manufacturing facilities. So wide usage. Telecom, utility substations. I won't read all of them, but batteries are really at the heart of all these industries and all these applications. So as such, it makes sense to be able to ensure health of these batteries. So when these critical backup systems are called upon, will they be ready? Let's take a step back from that and just kind of go through a little bit of terminology, a little bit of background on batteries. So we'll take a look at briefly at construction, some cell and battery types, advantages and disadvantages, before going into the specific measurements and tools needed to ensure battery health. So oftentimes, a battery, if we think of our car batteries, it's not just one physical battery. There's a number of cells inside that battery, often connected in series. And these series of batteries are referred to as strings. And the individual cells are around 2.2 volts. So if we think of our car battery, if you take 6 of those in series, that would give us 12.6 volts, would be a DC voltage that you would expect to measure on a car battery. Note that cells, those of you that have some battery test experience or been in the industry for a while, I learned that cells are often referred to as jars as well. So if you hear that term, that really it's the same thing as cells. So again, they're connected to provide voltage suitable for whatever the equipment is or whatever the application is. So those are some typical battery voltages, but you can then take batteries, connect them in series to give you much higher voltages for other applications. 48 volt, for example, for telecom. Different types of batteries there. I think you've seen all these. They all have advantages, disadvantages. NiCads, old technology, poor life, hazardous use. So they're banned. They're not used anymore. Replaced by the nickel metal hydride batteries for some application. Those are being replaced by lithium ion. They're less expensive than lithium ion, but they have a shorter life. Lithium ion batteries give you a high bang for the buck, high energy density, they're lightweight for their capacity. They are more expensive, but they're being used a lot more in small applications, wide variety of applications, including electric vehicle systems. A lot of battery backup systems are the workhorse really is the lead acid battery. And there's a couple of different types there. One known as wet cells, and those are the ones where you have to add distilled water or that hold electrolyte, and you can open them and then add that. Those are the kind of the original ones. Then there's newer ones called VRLAs, or valve regulated lead acid batteries. Those are the kind of the quote unquote maintenance free batteries where you don't add any electrolyte to them. They're sealed batteries. So that's a lot of what you're going to see. The flooded lead acid batteries, wet cells. They have some pros and some cons. Very high energy density. higher than the VRLAs. They also can operate under extreme conditions from a discharge. You can have some very severe discharge cycles, and it'll still have a good long life. They require regular maintenance, though. I mean, they have to be topped off with electrolyte. There's fumes present during the charging, so they're gradually being replaced, I think, in a lot of applications, at least what I've seen with the VRLAs. Those are the, and I'm going to use air quotes here, maintenance-free batteries. Again, they're sealed. We'll see in a minute. That doesn't mean they're maintenance-free. That just means you don't have to mess with electrolyte at all. A couple of those, there's a couple different types of VRLAs that are out there that designed specially so that you don't have to add any distilled water. Two different technologies that actually hold the electrolyte internally. And there's no fumes there during charging. But it's critical to have accurate charging current. Otherwise, it could shorten the life of the batteries. So I used air quotes. Here's the real quotes. Fact is, maintenance-free batteries require maintenance. Okay. No, you don't have to mess with electrolyte, but they need to be tested because they could be deteriorating internally in a number of different failure modes that are listed there. And we'll look at these in more detail in the upcoming slides. But as you see below, regardless of what's going on, the outcome could be a catastrophic battery failure, especially if you are not maintaining that maintenance-free battery. Again, there's different internal causes that could be happening. Inside the battery, thermal runaway, loose terminal and intercell connections inside the battery. Also, it can be from improper charging, overcharging, over discharging. If you have too much ripple voltage on your charging system, that can shorten the life of the battery. So as we get into the measurements, as far as, well, how can we ensure that the batteries are healthy and they're in a healthy environment from a charging perspective, we'll talk about those measurements and then the tools in a little more detail. But if we take a look at a battery and take a look at the graphics below, if you have a single cell go open, the entire string here goes offline and the load is no longer supported. So a single cell in a battery can have a big impact. And one bad battery also can affect the life of adjacent batteries by raising the charge voltage on the other batteries. So it really all points to, you need to do periodic maintenance to ensure the health of the batteries and the charging system. To that end, there are some battery maintenance standards. IEEE standard 1188, latest revision is 2014, really provides best practices for maintaining VRLAs in stationary applications. So as you can see, I'm not going to go through all these, but there's recommended inspections and a recommended interval. The measurements or the type of inspection and where you make the measurement are across the top. Things like voltage and current at the battery terminals, but also charger output, both voltage and current. Temperature, ambient temperature that the batteries are in. Heat and high temperature is one of the main enemies of batteries, can shorten the life. But also a health measurement we'll come back to is taking the temperature of the negative terminal on each cell. That can tell us any impending issue that might be coming up. We're going to be talking about internal resistance measurements and then also AC ripple on the charger. And for each of these, again, I won't read them. We'll be making the presentation available. It shows a recommended interval and what measurements should be made to ensure health at at the recommended interval. And then some guidance down below. So we'll take a look now at different things that or two different ways of assessing a battery. One is probably a way that more people are familiar, which would be a state of charge. And the way that you assess this is with a discharge test to find out how much charge or capacity is in the battery, how much energy can it deliver and for how long. It is an effective type of a test to determine capacity, but there's some downside there. One is it can shorten the life of the battery. Another is that it's an offline test, meaning the batteries are not available for service when you are doing this test. And the batteries can't be used, they have to recover, so they can't be used for a period of time after the test. So in a way, if you think about it, it's a lot more invasive and can have an impact on the batteries themselves. The trend more has been to go to what are called state of health measurements. So essentially, it's an online test, and you can perform that test while the batteries are available for usage. So you make those measurements while everything is online. And it's really an assessment of how much energy can the battery deliver from being fully charged comparing to the original spec. So we're going to look a lot more at the state of health measurements as we move forward. Main enemy, as we said, is heat. And those are some of the other issues: overcharging, things going on internally to the battery. We can't see those, but all of these effects, heat, overcharging, shedding, grid corrosion, we can essentially use a measurement to see if any of those or more than one of those is going on. Because in the end, we just want to know whether the battery is healthy or not. Don't exactly need to know, root cause, is it shedding, grid corrosion, etc. So as is indicated, the key takeaway here is all of these effects tend to increase the internal cell resistance of the battery. So that seems to be the best measurement that we can make to assess, are any of these things going on? So we would look at resistance. Briefly, we're kind of talking about internal battery resistance versus impedance. Really, it's the battery internal resistance. That's what reflects state of health. So the measurement that needs to be made would really be somehow to be able to isolate that internal battery resistance and not look at the reactive components such as an inductance or a capacitance that might be present. So again, key concept there: battery resistance is what is internal resistance, is what reflects state of health. And it enables us to be able to find hidden trouble spots. And over time, as some of these conditions that can cause battery failure are at play, we can look at resistance values over time to determine when should we trigger, or when should that trigger a maintenance or corrective activity, mainly replacing the battery. So keep that trending in mind. Trending is key. You can look at a trend, and then when you see a change in the slope of that trend, because battery resistance will remain relatively flat until end of life draws nearer, then it starts to go up. That's your trigger point to replace the battery. So that's really the right measurement, but used in the right way. It's that trending really is key. Fluke battery analyzers use a technique that isolates just the internal resistance. So we do inject an AC current signal. We are measuring an impedance, but through the measurement technique, we are able to extract just the R, or just the resistive component, the real part of the measurement, not the capacitive inductive part. It's a fast method. It lends itself very well to quick yet very accurate tests, making the right measurements. Kind of a key takeaway there is we're going to introduce a concept called a four-wire measurement or four-wire Kelvin connection to ensure resistance measurement accuracy. We haven't really discussed it yet. It's internal resistance that we're looking at, but the measurement ranges are in the milliohms range. So milliohms, tens or hundreds maybe of milliohms, so very, very low resistance measurements. Those of you that have meters, multimeters, you know that if you put the meter on ohms and you short the leads together, you have some test lead resistance there, right? You know, a couple tenths, 3-4 tenths of an ohm. When you are making measurements on something and you need to make accurate measurements way down in the milliohms, test lead resistance alone is much, much more than the desired measure value of what you're doing. So it's going to introduce a huge error. So somehow you have to be able to compensate for and negate the effects of that test lead resistance, you know, the way that you actually would interface with what you're measuring. So the way that you do that is through a Kelvin measurement. So two of the wires essentially are a measurement, you know, that supply test current, measure a voltage drop, but the other two leads sense the voltage drop across the other two wires. So if you know what the voltage drop is on your test leads, internally it can be subtracted from the actual measurement to give just the battery under test internal resistance. So it's a must to be able to make four-wire measurements. And here's what the probes actually look like to do that. This is one of the probes. There's both a red and a black, would look the same. So one of the poles here, the inner one carries the test current, and the other one is used to sense the voltage drop, you know, across the lead length, and they're insulated in between them. The probes need to be able to bite in, have good contact with what you're measuring. So every probe that we have has this same four-wire measurement. The tips can get worn down over time, so they're very easily replaceable. Plus, we do have angled probes that make it more difficult, or more simpler, I should say, to access difficult measurement locations. So for the Fluke battery analyzer features, we've talked about the probes. We're going to look more now into the key measurements that need to be made, and then also that lends itself very well to the business of battery testing, storing and documenting the data, and then analyzing the data, generating reports, something called a sequence mode. So we talked about battery internal resistance. That's key for state of health. But there's other resistance or other measurements that need to be made, you know, based on the IEEE 1188 standard chart that we looked at, DC voltages. Some of these voltages, depending on the applications, could be, you know, 480 volts, very high voltages. So it would be very useful to have capability to measure up to 1,000 volts in the tool, so you don't have to reach for a separate tool. Plus, you can use this tool to look at the AC side of a charging system, as well as the output side, DC voltage, as well as DC current. This tester also gives you capability of making a temperature measurement on the negative terminal of cells. It's done in the probes itself via a close focus infrared sensor. So that information is captured per the IEEE standard automatically for you. And then we learn that battery health can be adversely impacted by AC ripple. We can make AC ripple measurements as well as charging current measurements. So this is the complete kit, the BT521 battery analyzer. So let's take a look at the sequence mode. You know, why is this important? It's really about how somebody would do the maintenance work of walking through and testing all the batteries. The idea is to have a simple, fast, structured, repeatable means, paperless, so you don't have to write things down in the field, that one person could do, makes all the measurements automatically, or saves all the values internally to the tool. It organizes the data such that you're associating the right readings with the right cells in the right battery strings. And that's done via sequence testing. So you can actually create profiles, as is shown in the top screen, to put in site names, or if you are in different areas of the plants, device names. You can call it, certain UPS, or whatever it might be. You have control over that, so you can organize and sort your readings under that. You can have multiple strings, and per string you can have multiple batteries, so all that data is saved under a profile that you can use every time you test. So the process is, you would load in a profile, create it either in the tester or in the software that's included, go out, load in the appropriate profile, and then start measuring, which is what's shown down here. And the tester can automatically save readings for you in advance, and it'll show you what battery you're on, as well as how many batteries or cells are in that particular string. And then the goal is, you make your measurements, you come back to the office, you hook up by a USB, offload your measurements into the reporting software, where you can do those important trends, do an analysis, and generate hard copy reports if need be. So in that sequence mode, you can have a lot of different profiles in the tool. They can be created either in the tester or in the tool itself. Really, just about anything you would want to put in there to uniquely identify that profile can be put in. And then once you load in a profile to test, you begin the business of testing. And as you put the probes on batteries with the autosave capability, first it'll tell you what battery you're on, so which battery do you measure. It'll also show you what batteries you may have tested already, how many are in the string, and a number of other readings. So as you move through, the tester will automatically advance and point you to what is the next cell to test. As a convenience feature, the tester will also, for all of the measurements, all the cell measurements in a string, it will find what is the average of those cells. That can be very useful. I had mentioned trending, is one thing that's very important, but also you can determine a baseline for, they're working now, what's my known good? Or even with a new set or new string of batteries, by using the average of that string, that can establish a good baseline or a limit that you can actually use in the tester to kind of indicate pass-fail information just based on values. And as many batteries application might be multiple 12-volt batteries or 6-volt batteries strapped together, we can also, because they're interconnected, and that creates resistance. If you have a loose connection, that's a problem. So you can actually connect or switch between both strap connection measurements as well as battery cell measurements just by hitting the F2 function key. And once you come back to the office, then you can offload all that information by sequence. It's all stored and organized for you. Our top measurement here would be an example of using a limit that maybe we learned by that average measurement. and identifying any bad cells based on value. Down in our lower here, we see an example of how in the software we can trend those battery internal resistance values over time to look for that change of slope. And all of these measurements, everything that you do in the software with the measurements, you can add to a report and generate a very quick report, as well as creating profile sequences in the software that can be loaded into the tool itself. So in summary, maintenance-free batteries, they need maintenance. State of health really is a gold standard for online testing, and it doesn't impact battery life at all. State of charge does impact because you're doing discharge testing. So state of health is a great way of assessing health while everything is up and running. And one of the key measurements would be that internal resistance. You can establish the baseline by looking at the average of where you're at, and then using that as a limit. Also, trending is key. Battery analyzers, the Fluke BT521 is a great all-in-one tool, making all of your DC voltage, current, even AC voltage and current measurements in the charging system, making the internal battery resistance measurement the right way, enabling you to go about just the business of hooking up the probes, making the measurements. The tester will capture the measurement automatically if you want, and sort it, put it under the right string, the right cell, and then very easily be able to offload the data to trend and analyze to assess health. Well, I ran a little bit long here, so apologies for that. Not as much time for questions as we'd like, but time for questions. Sean, have they been putting some of the cat box?
Yeah, Dave, we've gotten quite a few. So everyone, it's time for you to take advantage of having an expert like Dave with us to answer any and all questions you may have. So please use the chat feature and send any questions. And please note that if there's any specific product related questions, such as pricing or availability, we encourage you to visit our website, globaltestsupply.com. There you're going to find a list of our products, pricing, technical specifications, as well as all our contact info, so the different ways you can connect with our technical support staff. We will be happy to address any and all questions you may have. Dave, I'll look through what we've got so far. What kinds of batteries can the Fluke BT521 test?
Good question. It's actually one that I've had some of our territory people ask me via customers, as well as customers ask. It's really battery independent. So all the different types of batteries that we covered can be tested with the BT521.
Great. Got another question here from Nick. What would be a good battery internal resistance measurement value?
Probably the most often asked question that I get. So I think the best approach is to take the practical approach that we discussed. You might be able to get data on that on a per battery basis from manufacturers, but those numbers are going to depend on that measurement technique we discussed. You know, is that number including both resistance and impedance? But you really don't want the impedance portion, you want just the resistance. So really a practical approach is either on new batteries, kind of learn what good looks like. Again, take the average of strings and use that as a known good. If you don't have new batteries, you got to start somewhere, you know, where they're working now, kind of again, take that average of all the measurements, the internal resistance measurements in the string, and you can use that as limits to identify outliers.
Perfect. Enrique, to answer your question about the saved webinar, we will be emailing you all a copy of this webinar for later reference. So you'll get that in your inbox in a couple days. Donald, you have a great question, actually. It's something that I'm wondering as well. Donald's asking that the third-party commissioning agent that he has uses the 1750. What would the advantage of using the new 1777 be?
That's a great question and very relevant. I think in 1750 was a great tool and a great tool for that. The operative word there is was. The 1750 is no longer available. 1777 offers all the horsepower in the 1750 and more, then some. It's actually 4 times faster transients can be detected. It's much easier to use setup than the 1750 was. 1750 was primarily set up from a software interface, a laptop, whereas 1777, you can do all your setups right on the tool, right where you hook it up. And then it's got great analysis software. Again, that's bundled with the tool, free download on the software. And I think it's better software too, in my opinion.
Awesome. Yeah, I'm really excited for that one as well, actually. We have another question that just came in from Jordan. What is the recommended frequency of battery testing? Is this best determined by the manufacturer?
The IEEE 1188 standard actually references that for VLRA batteries in general. I'm going to kind of put that screen or that slide back up. Can you see the battery maintenance standard?
Yeah, I see it there.
Okay, great. Yeah, and if you want to do a screen capture on that, any of you, I think you probably can. The battery manufacturers might also have recommendations. I don't have as much experience working directly with the manufacturers' recommendations, but I know this is the best maintenance practices standard, essentially.
Excellent.
What measurements and how often to make them.
Yeah, and everyone, if you want to grab a screen grab of that, you will get a copy of this webinar later on as well. But in the meantime, that might help you, Jordan. If there's any questions that you haven't had a chance to send yet, or we haven't fully answered that you'd like more responses on, please feel free to send us an email at sales@globaltestsupply.com. And any other questions we don't get to, we will follow up with you later on. So I think that's about all the time we have today, unfortunately. On behalf of Global Test Supply University, we thank you for attending our webinar today, and we hope that you found it informative and helpful. Global Test Supply is available to assist you in any way. Simply visit us at globaltestsupply.com for anything you need. Through Global Test Supply, you will have access to our entire list of Fluke products with descriptions and specifications. You will also find our contact information in order to contact and connect with one of our technical support staff who are able to answer any and all questions you may have. At the end of this webinar, we do have a very short survey that we'd like you to complete because your feedback will assist us in improving and allow us to bring you more topics that are of interest to you. We have upcoming webinars in the next few weeks and months, so please visit the training section on globaltestsupply.com for a full schedule of the upcoming webinars and topics. And don't forget that as a thank you for attending our webinar today, your name will be entered in a draw to win $100 for your next online order. The winner will be announced on our social media channels, so please be sure to check us out there. Dave, thank you so much. Super informative webinar as always. And I hope you all have a great rest of your day.
Thank you, Sean. Thanks, everybody. Have a great day.